Welcome to this explainer. Today, we're popping the hood on a totally revolutionary computational engine that's completely rewriting the rules of computer graphics. I'm talking about 3D Gaussian splatting. For decades, achieving photorealistic, real-time 3D reconstruction just felt like an impossible dream. But today, we're actually diving into the architecture making that dream a reality. We're going to look at the exact code and algorithms powering the virtual worlds of tomorrow.
Okay, let's quickly hit our roadmap. We're going to cover the 3D rendering revolution, take a look under the hood, talk about upgrading primitives, optimizing the pipeline, scaling to brand new dimensions, and finally wrap up with the future of graphics. Let's get right into it.
So, Section 1, the 3D rendering revolution. This is a massive paradigm shift. This shift literally forced graphics researchers to completely rethink how we build explicit 3D scenes from the ground up. Look, for a while, neural radiance fields, NeRFs, were the absolute gold standard, right? They gave us that picture-perfect volumetric quality, but man, they were sluggish. Because they relied on really expensive backward ray tracing, they were computationally intractable for anything interactive. But then, on the right, we have the new heavy hitter, 3D Gaussian splatting. It achieves that exact same state-of-the-art photorealism, but crucially, it does it in strict real time. And it pulls this off by ditching those heavy neural network queries entirely, swapping them out for forward-mapping explicit primitives.
So, what exactly is it? Well, mathematically, we're looking at scenes represented explicitly as unstructured collections of millions of anisotropic 3D Gaussians. These are then rendered via a tile-based differentiable rasterizer. Now, to conceptualize this without getting bogged down in the intense math, just think of these 3D Gaussians as millions of fuzzy, semi-transparent directional paintballs, dynamically filling up a 3D space. They've got position, shape, color, transparency, and they blend together so perfectly that they form what looks like a completely solid, hyper-detailed world.
All right, Section 2, under the hood. Let's look at the mechanics of 3DGS. Now that we've got a scene made of millions of these fuzzy paintballs, let's check out the engine actually putting them on your screen at real-time speeds. This sequence is basically the heartbeat of the framework. It's a highly optimized tile-based rasterization process that acts a lot like a high-speed factory line. Step 1 is projection, taking that 3D shape and mapping its footprint right onto our 2D screen. Step 2 is tile binning. The screen gets chopped into a 16 by 16 grid of macro tiles, and if a projected Gaussian overlaps multiple tiles, it just gets duplicated and assigned to each one. Step 3 is sorting. Within every single tile, the engine runs a lightning-fast radix sort to order the Gaussians by depth. You gotta know what's in front of what, right? And finally, step 4 is blending, where parallel GPU processors cooperatively accumulate those colors pixel by pixel.
Moving on to Section 3, upgrading the primitives, moving beyond ellipsoids. As amazing as those standard fuzzy paintballs are, what if a basic elliptical shape just isn't the right fit for, say, a razor-sharp edge or a perfectly flat wall? Well, researchers have built some absolutely wild aftermarket mods for these primitives. Standard Gaussians are beautifully symmetric, sure, but the real world isn't. So we get the skew Gaussian, which adds directional asymmetry to perfectly fit slanted, complex surfaces. Then you've got the half Gaussian. This introduces a strict one-sided cut, which lets us model razor-sharp hard boundaries without that typical blurring effect. We're even seeing the student's t-distribution being used to create a heavy tail effect, making the whole scene way more robust to visual outliers. And for perfectly flat walls, researchers are actually collapsing that 3D volume into flattened 2D circles for geometrically consistent surface extraction. They're literally changing the shape of the brush to match the canvas. It's brilliant. Okay, Section 4, optimizing the pipeline, where we solve the bottlenecks. Because here's the thing. Dealing with millions of these newly upgraded primitives creates a massive traffic jam in the engine's hardware. The tension here is super real. Remember that fast radix sort we just talked about? Well, running a per-tile radix sort on millions of overlapping splats every single frame is an immense computational burden. It totally saturates the GPU's memory bandwidth and creates severe rendering latency. Plus, and this is the worst part, if the depth sorting is even slightly off between frames, you get these highly distracting view-inconsistent popping artifacts. Parts of the scene will just suddenly jump over one another. If you've ever played a game where a texture randomly glitches over another, you know exactly how annoying that distraction is.
But incredibly, researchers have figured out a way to aggressively trim the fat. By using algorithmic pruning techniques, essentially pinpointing and tossing out redundancies with methods like MMGS, they can actually cull over 80% of a scene's initial Gaussians. 80%! Imagine taking a car engine, removing 80% of its moving parts, and having it somehow run better. It's crazy.
And the crucial takeaway here is that this aggressive reduction isn't just about saving memory. It actually acts as a geometric regularizer. By forcing the scene to be represented by far fewer primitives, it inherently suppresses all those high-frequency artifacts and that floating visual noise. The visual fidelity, which we measure as peak signal-to-noise ratio, or PSNR, actually improves right alongside the rendering speed. It's basically the ultimate proof in graphics that sometimes less truly is more.
Section 5. Scaling to new dimensions. Let's talk 4D and city scale. So how do we take this incredibly optimized lightweight engine and apply it to moving objects, or even massive, unbounded city-scale environments? The secret is structural evolution. For 4D dynamics, scenes that actually move over time, we're seeing methods like deformable 3D Gaussians. These use tiny neural networks, MLPs, to predict how each splat gets displaced frame by frame. Or there's spline GS, replacing jerky, discrete movements with smooth, physically plausible spline trajectories. But what if the scene isn't just moving? What if it's the size of an entire city? That's where spatial partitioning steps in. Scaffold GS anchors scene content to sparse voxel grids, meaning it only allocates Gaussians where things actually exist, totally ignoring empty sky or hollow spaces. Meanwhile, Octree GS organizes all that city-scale data into multi-resolution pyramids, dynamically dialing the level of detail up or down depending on how far the camera is from the object. Finally, Section 6. The future of graphics. Lightweight and unified. This brings us to the ultimate triumph of the field, making these massive, photorealistic scenes compact enough to actually use in the real world. Because let's address the elephant in the room, the data weight. Initially, a single static scene in the original 3D Gaussian splatting architecture would cost you around 700 to 800 megabytes of storage. That is an absurdly heavy data footprint. I mean, if you want to stream a game straight to your phone or load an environment into a standalone VR headset, you absolutely cannot have single static rooms eating up nearly a gigabyte of space. But check this out. We are now seeing a staggering 15 to 20 times reduction in file size, and this is just over the past couple years. We're going from those original 800 megabyte files down to 200 megabytes using those hierarchical structures we just mentioned, all the way down to a tiny 40 megabytes. 40! They're doing this using advanced compression architectures like HACC++ and standardized formats like LCC2. By combining interpolated hash grids, parameter quantization, and context-aware arithmetic coding, these massive, unwieldy files are being completely transformed into lightweight assets you could stream instantly.
To wrap up this explainer, I want to leave you with a thought. We've seen how 3D Gaussian splatting shattered the rendering speed limit, how primitives are being custom reshaped for perfect geometry, and how file sizes are being crushed into these ultra-lightweight formats. And research is already showing we can embed AI semantic features right into these splats, meaning the engine can actually understand what a chair or a wall is. So I have to ask, what will video games, virtual reality, and robotic simulation actually look like when this ultra-fast, photorealistic engine natively understands complex 4D physics and human language intelligence, all computed simultaneously in a single pass? We are quite literally looking at the foundational matrix for the next generation of digital realities. Thanks so much for joining me, and keep exploring.